get going. So, the exam under preparation and will be distributed. I'll send it via email, so in case someone's not at the problem session, you can get it there. We'll have a discussion section on Friday, usual, to discuss any community questions. So the main point of in terms of the rules of the exam is that you're allowed to use any resources you want for the take-home exam as long as you reference them. Okay? And that includes the internet. I mean, that's available to you. There's web pages you use, in books, etc. Of course, you're allowed to use any of the course materials, the notes, the homework, the homework solutions. That's all accessible. Basically, all resources are allowed except human resources. Okay? That means you are not to discuss the problems with anyone else. Okay? And that's the very strict rules. Okay? So there is to be absolutely zero discussion between you or with any other professor or anybody else about the problems. Okay? Other than that, that also includes no Skype conversations. Okay? Phone calls, Twitters, what have you. Nothing. All right? Okay. So, let's see. So last time we were talking about solving the Schrodinger equation, the time-independent Schrodinger equation, in the case where we're looking at a problem with more than one degree of freedom. Okay? So the Hilbert space for the system in that situation, as we discussed, is a tensor product space of the Hilbert spaces associated with each degree of freedom. However, we decide to define those degrees of freedom. As I mentioned, this decomposition is not unique, right? It depends what degrees of, I have two particles, I could talk about the motion of each particle, or I can talk about their center of mass and relative coordinate, for example, okay? The joint Hilbert space is unique. It's the span of all of these product states. So we're looking to solve the time-independent Schrodinger equation. Let's say we're looking for the energy eigenvalues given the Hamiltonian on this system with some number of degrees of freedom. We said that there's a particular case that's very nice if we can arrange it for some choice of the degrees of freedom, if we can separate the Hamiltonian into a Hamiltonian that only acts on degree of freedom A, degree of freedom B, etc. When that's the case, then the solution to this problem can be broken up into, or separated into, a separate eigenvalue equation for degree of freedom A, one for degree of freedom B, etc., etc. Okay? And when that is true, then the joint eigenstate of the system is just a product state of the eigenstates for each of the degrees of freedom, and the total energy eigenvalue is the sum of the energies for each degree of freedom. Okay? And this would be true, I mean, for other kinds of eigenvalue equations, not just for the Hamiltonian. If I have some Hermitian operator, some observable, which can be written as the sum of observables on the different degrees of freedom, then the same logic holds, right? Okay. Another thing we talked about, an important concept, is the relationship between symmetries and degeneracies of the system. So in where you have multiple degrees of freedom, when we talked about in 1Ds, particularly if we have bound states of, in the case of bound states, what we proved in 1D, there are no degeneracies, right? That's impossible if you unless you have infinite walls that you get like two infinite wells, right? Then you could have in 1D degeneracy, but generally you can. But in multiple dimensions, even the bound states can, and we know that. Think about, for example, the hydrogen atom and so forth, which we'll get to someday. We do have degeneracies, and there's an intimate relationship between degeneracies and symmetry in the system. So if the Hamiltonian is invariant under some symmetry operation, and that symmetry operation is implemented in quantum mechanics by some kind of unitary transformation on the system, then, well, what that means, firstly, is to say that it's invariant, is to say under the unitary transformation, the Hamiltonian comes back to itself. And that's equivalent to saying that the Hamiltonian commutes with the unitary transformation, right? And if that is true, then what that says is that if this is an eigenstate of the Hamiltonian, then so is this with the same eigenvalue. That is to say, these two states are degenerate. And that follows from just applying the Hamiltonian to this ket. If this is an eigenvector of the Hamiltonian with that eigenvalue, then if I operate the Hamiltonian on the unitarily transformed vector, because this commutes, I can bring it through and I get that eigenvalue. So that means that this vector is an eigenvector of H with the same eigenvalue. So these two vectors have the same energy eigenvalue. They're degenerate. So if I have a symmetry, I will have degeneracies in the system. Okay? And those are called essential degeneracies of the system. All right. Now, we were looking at some particular problems, examples in this last time. We looked at, for example, the square well. Well, we looked at a couple of problems in 2 dimensions. One we looked at was this, an infinite square well into 2D. Or you might, I should call it a rectangular well. Because it doesn't have to be square. It could be a rectangle in this particular case. So I have some width in X, width in Y, and there's infinite walls outside there. That's a separable problem. As we discussed, the kinetic energy is always separable in X and Y. And whether or not the Hamiltonian is separable depends on whether the potential is separable. Okay? And in this case, it is separable in X and Y, and thus the energy eigenvectors separate into eigenvectors for excitations along X and excitations along Y. And the energy eigenvalue is just the sum of the eigenvalues associated with the 2 square wells, right? And if I had, as I was saying, before I got to the finally, after stumbling about, sadly, on cyberspace forever, I'm going to tell people to erase that one. They're more embarrassing anyway. If we have, for example, this case, then there is in that particular case is an example where we have accidental degeneracies. There are just cases where there are two different sets of quantum numbers that give the same energy eigenvalue, even though there's not a symmetry in this problem. So that can happen just by accident. Okay? And because it happens just by accident, it's kind of hard to find them, unless you can just, just look at this quickly and see. This is an example of these two sets of quantum numbers. You get 20 for both cases. Okay? All right. So, on the other hand, if we had Lx equals Ly, if we had an actual square, in that case, then in that situation, there's an essential degeneracy. And that essential degeneracy arises because there is reflection symmetry. So if I interchange x and y, the problem looks the same. And because of that reflection symmetry, there is an essential degeneracy. And that is to say that the energy eigenvalues are the same whenever I switch the quantum number for x with the quantum number for y. So the case, for example, nx equals 1 and y equals 12 has the same energy as nx equals 12 and y equals 1. Right? It's obvious. This is symmetric in x and y. So any time I switch those quantum, there's degeneracy in the problem. Yeah?
So, that square has, lots of different symmetries, but we're looking for the symmetry where it can switch coordinates? Or I'm kind of...
Sure. Well, in this case, it has, as you say, I can reflect it around this axis. I can also has parity symmetry. So parity is another symmetry of the problem. If I change x to minus x and y to minus y, that is another symmetry in the problem. Okay? Now in that case, that doesn't give me a degeneracy in the system. It just, but we do know that it must be the case that eigenstates of parity are also eigenstates of energy. Let's say the energy eigenstates are parity eigenstates. Right? So that's a symmetry within a degree of freedom. A symmetry that affects the different degrees of freedom can lead to degeneracies. Okay, good. So the other problem we were talking about was the simple harmonic oscillator in 2D. Okay, and in particular, let's consider the case that we have isotropic binding. Okay, so if we have isotropic binding, then so here's my coordinate system x, y, and if I'm displaced from let's say the equilibrium point is at the origin. So in cylindrical coordinates, I have a rho and a phi. Then we're looking at the situation where the potential of this system is only a function of rho. It doesn't depend on phi. Okay? It's got minus the force is this, so the potential is 1/2 kappa rho squared. Right? That's the potential energy. Or 1/2 m omega squared rho squared, which is 1/2 m omega squared x squared plus 1/2 m omega squared y squared. Is that clear? So in this situation, we can separate, the Hamiltonian for this problem, right? I can write it in terms of x and y motion, or equivalently, I can write it in terms of radial momentum and tangential momentum. Okay. Where I can have momentum along rho and momentum along phi, if I like, right? So this problem is separable in two different sets of degrees of freedom. In principle, I could separate it in terms of motion along x and y, or I could separate it in terms of motion radially and tangentially. Okay? So we can write down, in this case, for example, the energy eigenfunction. Suppose I choose to separate this. So I'm looking for the energy eigenvectors and eigenvalues. This problem is separable in x and y. So I can write the solutions as the harmonic oscillator along x and the harmonic oscillator along y, right? So if I separate in x and y, then my eigenvectors, energy eigenvectors, I can write as this, where each one of these corresponds to a number of harmonic excitations, either in x or y, right? And the energy eigenvalues, given those two quantum numbers, is h bar omega nx plus a half plus h bar omega ny plus a half, or h bar omega nx plus ny plus a half. I'm sorry, plus 1. Now, we see in this case that, in fact, the energy eigenvalue, or the energy eigenvalue in this case doesn't really depend independently on x and ny, but only depends on the sum. Whatever the sum is determines the energy. So any pair of eigenvectors which have the same sum have the same eigenvalue of energy. So there's some quantum number n. This could be 0, 1, 2, depending on that value. And there's a degeneracy. So there's a degeneracy. That is to say, the energy here really only depends on some quantum number n. The energy is h bar omega n plus 1, with the degeneracy. Well, what is the degeneracy in this case? How many different ways can I take an integer n and divide it into the sum of two integers? Well, this is like the number of balls, and you know how many boxes. You have to count it. I hate counting birds. I'm so bad. All right. So why is there a degeneracy here?
Does that do with the reflection?
There is reflection symmetry here, But there's more than reflection symmetry here. I mean, it's true. This is absolutely, if I switch x and y, there is reflection symmetry. But there's a broader class of symmetries here.
Radial?
Or what we call, it's actually azimuthal. It's rotationally symmetric. This Hamiltonian, the potential is independent of phi. Okay. So really this degeneracy is stemming from rotational symmetry. Okay. The rotational symmetry is saying that the Hamiltonian, if I rotate this, let's say let u phi equal the rotation operator, which we'll discuss in a moment, about the axis by angle phi. There's a rotation in real space as opposed to the rotations in phase space that we were talking about. It's in 2D space. So this Hamiltonian is invariant under such a rotation. And the reason that's true, well, the kinetic energy is always invariant under a rotation. But the potential here is independent of phi. Okay? The potential is azimuthally symmetric. Right? I mean, this potential, if we were to sketch it, it's a, so here's the xy plane, and the potential as a function of x and y is, of course, a parabolic well that is azimuthally symmetric. You see my beautiful picture? Okay, so because of this symmetry, we expect degeneracies in this problem. Okay? Now, notice, however, there's something a little bit, these are perfectly good energy eigenvectors. Okay? They are. We operate the Hamiltonian on them, you get back this energy. So these are good, these are perfectly good energy eigenvectors. Now, unfortunately, my damn computer crashed. I was going to show you a picture, so I'm going to have to attempt to sketch it. It's going to be a disaster, but let's try. So the energy eigenvectors suppose I look at this in the position representation. Okay, that's the position. This is psi and x and y as a function of x and y. And that's just, the energy eigenfunction along x and the energy eigenfunction along y. Okay? And those we know, in dimensionless units are some Hermite polynomial along x, e to the minus x squared over 4, and some Hermite polynomial along y. Dimensionless. Right? So this is so what do these wave functions look like? Well, if I look at, for example, the ground state is non-degenerate, right? And for the ground state, this is and 0, this is a constant, and then that's just a 2D Gaussian, right? So for the ground, I'll draw this as a kind of contour plot, because I don't want to attempt to draw my attempt at perspective is ridiculous. So here we are in the xy plane, and there's, the wave function here will be a Gaussian. Okay, this is not the Wigner function. This is the wave function in 2D. Of course, I could write a Wigner function in 4D, but I'm even going to tend to try to draw that. Yeah.
Well, it's not the Wigner function, but it has the same shape.
Exactly the same
Okay,
shape.
okay.
It's the same shape. Exactly. Okay, what about the first excited state? Well, there are 2 of them. The degeneracy in that case is 2. And so we could have the first excited state, we could have 1 excitation along x and no excitation along y. So what would that look like? Well, along x it has a node, and along y it looks like a Gaussian, right? So it's something which has kind of a double hump like this, where one of these guys is positive and the other is negative. Is that clear? And then if I have the other way, then I have 1 excitation along y, I have a node along y and no nodes along x, with this guy plus and this guy minus. Okay. Now, here's something I want to emphasize. These states are not rotationally symmetric. This guy clearly looks different along x than it does along y. And this guy clearly looks different along x than it does along y. So these are not rotationally symmetric. How in the world is that possible? When we said that the Hamiltonian commuted with rotations around the z-axis, and thus we said that if we can find simultaneous eigenstates of the rotation operator and the Hamiltonian because they commute. Yeah.
And so this is like a basis though? So would the actual, would have to be a superposition of all of those or no?
So, okay, so you're on the right track. This is a perfectly good state of the system. This is a stationary state. This is an example of what we call a symmetry broken state. That is to say, when we have degeneracies, there exist eigenstates of H which are not, there exist, which are not eigenstates of the symmetry. Why? Well, let's come back to the front door over here. What we showed here is that if the Hamiltonian commuted with the symmetry operation, then this and this are degenerate. But it didn't say that this was necessarily an eigenstate of U. They could be different states, but they will have the same energy eigenvalue. Okay. Now there exist simultaneous eigenvectors, but there also exist ones that of U and H. But it doesn't mean that we can't have states that are eigenstates of H that are not eigenstates of U. We talked about this a little bit at the very beginning of the semester when we talked about mutually commutative sets and block diagonalizing. Like, what the hell was he talking about? No idea. This is an example of that. So if you look at this picture again, this state is a rotation by 90 degrees of this state. So in fact, this is an eigenstate too. With this and this. Now, as Zeke suggested, I can take any superposition I want of degenerate eigenvectors, and they are also an eigenvector with the same eigenvalue. So, for example, if I define psi as C nx and y. Oh. Let me define this. C 0, 1, 0, 1 plus C 1, 0, 1, 0. Okay? Where this is an x and this is an y. Is this an eigenvector of the Hamiltonian? Yeah. And it's the first excited state. Because the first excited state is a two-dimensional, any state which is spanned by these two states is also an excited state. The excited state defines a two-dimensional Hilbert space in the whole Hilbert space. Anything which is a superposition of these two is a first excited state of the system. Okay. This is n plus 1, right? So this is 2. Okay, so that's one lesson. When we have degeneracies, it can be the case I could choose to define eigenfunctions or eigenvectors which do not respect the symmetry. They're called symmetry-broken states. And you might have heard about spontaneous symmetry breaking, elementary particle physics, it's really just this. You can have ground states. If you have big degeneracy, you can have states, for example, ground states that don't respect the symmetry. They're symmetry-broken states. Okay. However, we can also define states which do respect the symmetry. We can. They are obviously superpositions of these guys. So there exists, for any energy level, in this case the first excited state, there exists coefficients, you're going to have this problem for homework, which enforce rotational symmetry. Okay? So we can find those directly by separating, so the rotationally symmetric eigenstates are separated in rho and phi. So I can have, in this case, Remember, my Hamiltonian in this case we said was radial momentum plus the radial potential, and then tangential momentum. And they're operators on these guys. So if I can separate this into some eigenvector along the radial direction and eigenvector along the tangential direction, then I can define attributes of symmetry. Let's talk about that. So, if I look at this Hamiltonian, the fact that the potential is independent of phi, so classically, that means that the tangential momentum is conserved. Right? If you wrote down the Lagrangian and do all that stuff. Right? So the tangential momentum is conserved. That is to say, why is this true classically? Well, if it's independent of phi, only depends on the distance, we call this a central potential. The force is central. It has no push tangentially, which is a central potential. That is to say, there's no torque on the system. So we can't change the tangential momentum. Okay. We know that the tangential momentum of the system is nothing more than the z component of angular momentum over the radial distance. So Lz here is the z component of angular momentum. So the fact that we have a central potential is an equivalent to saying that this Lz is conserved. As we discussed, as we know from Noether's theorem, classically, if you have a symmetry, there is a conserved quantity. The symmetry here is rotational symmetry around the z-axis, and that the conserved quantity is the z component of angular momentum, which just means there's no torque on the system. I mean, this is still physics. All right, but in quantum mechanics, we have another connection here between symmetries and conserved quantities. And that is that the conserved quantity is the generator of the symmetry. So now let's talk about quantum. What we could still say is that Lz is conserved. And that means that Lz is the generator of rotations around the z-axis. Okay. So, well, can we see that that's clearly the case? Let's write down the momentum operator associated with the tangential momentum. Okay? So what is this? Well, this is equal to h bar over I in the position representation times the derivative with respect to the distance along that coordinate. That's the momentum operator, right? If this were x, y, or z, this would be p sub x. This would be. And what's the distance along that? Well, that's, r phi. So this, in curvilinear coordinates, is this. Okay. So from this, we see in the position representation, LZ is the derivative with respect to the phi coordinate. And that means that this is the generator of displacements along phi.
Why is momentum and phi be dependent on rho over there?
Because if I have the displacement along this lane here, if this is phi and this is rho, then this lane, or if this is a little d phi, delta phi, then this lane is rho delta phi.
Well, I'm just curious whether you wrote the rolling momentum under the p of phi is conserved. Shouldn't that be p of rho underneath it equal to?
No, it's d of phi. It's the tangential momentum. The radial momentum is not considered. The tangential momentum is considered. Right? So we remember we had the derivative with respect to x was the generator of displacements along x. Momentum is the generator of displacement along x. A derivative along phi is the generator of displacements along phi. Okay? So we can, given this representation, we can ask about, let's think about our separation of coordinates in for the Hamiltonian in this case. Okay, so I can rewrite the Hamiltonian. So for my 2D simple harmonic oscillator, I can rewrite my Hamiltonian as radial momentum and the potential plus angular momentum over 2m radius squared. Okay. So now I can look for energy eigenfunctions. Of the form some radial wave function and some, I'll call it, angular wave function, separated angular okay. Separated in the cylindrical coordinates. And what I want these guys to be is they should be eigenvectors of LZ. Okay? So we seek eigenvectors of LZ. Well, that's something we can solve in position representation immediately. Let's look at this in position representation. So I'm going to call that eigenvalue m. Let me. Oh, I'm going to get confused with the notation here. So let me call that eigenvalue capital lambda. Okay. So this we said was h bar over I d by d phi capital lambda what is capital lambda? Well, what we see here is the eigenfunctions of the system. We can immediately solve this differential equation, right? That differential equation is, sign is bothering me, but I guess. There's something wrong with this sign. Oh well. This is backwards.
You want decaying exponential?
No, it's whether it's either the plus side or either the minus side. And I'm pretty sure I want either the minus side, but I'll have to go back. So I think I have it wrong in my notes, so that's why we'll leave it as this and we'll come back to it. Because this eigenvector, this eigenfunction here is equal to h bar over I lambda phi. Right? When I take, the other way around. Okay. Take this derivative with respect to phi, I get it back. So these are my energy eigenfunctions. In fact, we typically call this h bar times a constant m. Okay? So my when this thing acts on this, is the generator of rotations, and therefore it generates displacements along phi, then the eigenfunction of angular momentum should be something that looks like just a phase, as to say the probability amplitude should be independent of phi. In the same way that a displacement along x, the eigenvectors of displacement along x, are e to the ikx. They're plane waves in x. This is like a plane wave along phi. All right? And if I want to normalize it, how do I normalize it? Well, here phi goes from 0 to 2 pi. And that has to be 1, so I better write this as square root of 2 pi for normalization. Right. So, what that says is that the energy eigenfunctions for the 2D simple harmonic oscillator, I could write as having a radial quantum number and an angular momentum quantum number. It has some radial wave function, and then the angular momentum wave function. Question: is this thing azimuthally symmetric?
Yes.
Yes. I mean, in particular, what's true is that the square of the wave function, the probability to find the particle somewhere in the well, is independent of phi. Okay. Of course, there's this phase here. So the phase is important. In this case, it depends on phi. But it's an eigenvector of rotation with eigenvalue m. This state, of course, I should be able to make this out of the eigenvectors along x and y, because we said they form the basis for the system. Right. So, just for fun, what do you think those wave functions would look like for the first excited state?
What they always
Well, what do you mean? What do they always look like?
show 2 points, 2 a max and a min.
Well, it's got to be azimuthally symmetric in the xy plane. Let's go back to this picture over here. So this was the eigenfunction along with one excitation along x. This was the case where we had an eigenfunction along one excitation along y, 0 along x. What is the wave function associated with one excitation, but it's azimuthally symmetric in x and y? What it's going to look like in that case is a donut. It has a node right in the middle. It's got to have one node. So we're just taking this and making it azimuthally symmetric. Now, those of you who work in optics may be familiar with these kinds of things because the transverse modes of a laser beam can be expanded in these bases. It doesn't matter when I'm talking about classical waves or quantum waves. The mathematics is the same. These kind of modes are called TEM modes, 1, 0, 0, 1. And these are Laguerre-Gaussian modes, which are donut modes. Let's see this. All right. So we've come to an important juncture in the class. We have this important symmetry, rotational symmetry. Yikes. You can take that and bring a little grease. So, fair play.
That was my idea.
All right. So, we've come to have an important new symmetry here. What we have is that angular momentum is the generator of rotations. So in particular, what we just saw just now is that the z component of angular momentum generates rotations around the z-axis. Oh, I guess there was an important point before I get to that, which I really meant to emphasize. Come back here. So let me back up for a moment. What are the allowed eigenvalues n here?
To make L positive.
Well, ultimately we know that, but just looking at this, just from what we did at the moment, just solving this differential equation, what are the allowed values of n?
They have to have continuity when you go all the way around from 0 to
Exactly.
pi.
So we have to have it the case that this wave function at phi has to be continuous when I go around by 2 pi, right? Which means that this has to equal 1. So what are the allowed values of n?
Integers.
Integers. Integers, not half integers, not half integers. That's not allowed for rotation, the generator of motion around the z-axis. So in this case, what this says, if these eigenfunctions, m as being an integer, can be a positive or a negative integer, but it has to be an integer. Okay. All right. So now back to our programming over here. So it's a generator of rotations around the z-axis. And from just now thinking about this from the point of view of our abstract algebra, not necessarily the representation in position space, we have developed a little bit of formalism here to say what are the necessary commutation relations of the different observables given the fact that this is a generator of a symmetry. How do we see that? Well, if this is a generator of rotations around the z-axis, what that means is that this is the rotation operator. And to get the commutation relations, we look at infinitesimal rotations, the generators of those rotations, things that are near, close to the identity. So if I look at some vector that say is along the x-axis, and I rotate it by a little amount, delta phi, around the z-axis, then I should add a little bit along y. Okay? So if I rotate by delta phi around the z-axis of x, that should become x plus delta phi y. In the, the vector, the x. If I rotate around the z-axis. So how do I see that? Well, let's look at an infinitesimal rotation around the z-axis of x hat dx. Let's look at the x coordinate. So if this is an infinitesimal, I can write this as 1, the dagger is 1 plus I, delta phi, LZ x is 1 plus I, or minus I, delta phi. So this is my infinitesimal transformation, right? And if I write this out, I get x hat plus I delta phi over h bar LZ times x minus x times LZ, so the commutator. And what that tells me thus is that it must be the case that the commutator of LZ with x is equal to IH bar y in order to generate that rotation. Similarly, if we went through it, we would go and find that the commutator of LZ with y is I is minus we saw that. That certainly works because the component of angular momentum is related to the components of x and p, right? So if I look at the angular momentum vector as x cross p, then LZ is xpy minus y px, right? And if I commute this with x, well, then I get that this commutes with both of these guys. X commutes with x. X commutes with py, right? X commutes with y, but x doesn't commute with px. And the commutator, so this is minus y, the commutator of px with x. And what's that?
Minus I.
Yep. So it all works. So it's self-consistent. LZ is the generator of rotations around the z-axis. Now we would like to do this more generally in 3D. So, 3 dimensions. So let's say I have, what I want to define now, what I claim is that n dot L is the generator of rotations around the axis n. Okay? So if n were the z-axis, then this is LZ. If n is the x-axis, or any direction in space. That is to say, given an axis and an angle, my rotation operator is that. So this is the operator that rotates me about the axis n by the angle phi. Okay? Just like this operator here. This rotated me around the z-axis by the angle phi. Okay? This is more general than this. So now that's to say I have a position vector. Here it is somewhere. And I have some axis of rotation. Okay? So there is a plane here. This is the normal to that plane, sort of. Okay, so this n is normal to this plane. And what it does is it rotates me by that. So it takes this vector, the vector that is in this plane, and translates it a little bit. Okay, so I take that and I rotate it by some amount in that plane. And take this vector to the new vector, x prime. So it's a rotation around that axis by this angle. Now if this is a infinitesimal rotation, a very small rotation, then this little vector that I add to me is n hat cross x. N cross x is perpendicular to both n and x, and is the little displacement that I'm doing in a rotation. So under this, an infinitesimal rotation by this amount, then what I expect is that if I rotate by some small delta, take this x hat, what I should get is x plus n cross x times delta phi. Okay? So that's a small displacement. That's like if we rotate around the z-axis, then x goes to x plus y, right? Z cross x is y. All right, what does this say about the commutation relations then? Well, we could go through this exact same exercise that we did over there. This tells me that 1 plus I over h bar times delta theta and dotted into L, the position vector in 3D, 1 minus I delta theta over h bar and dot L hat is equal to x plus delta phi n cross x hat. All right? So now again, the identity part cancels the x. I keep the terms only to first order in delta phi, because I'm talking about an infinitesimal rotation. And I combine all the terms, and I get the following. The component of angular momentum along n, commuting with the position vector, is equal to minus I h bar n cross x hat. Okay, so now that's just, can't combine all those terms, doing the same thing we just did. If I look at this in component form, then it's a little work, but not a lot. You can quickly show what this says is that Li with xj is equal to I epsilon ijk xk, sum over k. Similarly, so that means, Lx with y is I h bar z, etc., etc. You did this for homework, right? But now we're seeing it from a different perspective, just from the perspective as if it's going to be the general rotations around an axis, it must satisfy these commutation relations. Indeed it does. And it's true for any vector. For example, momentum also satisfies this kind of commutation relation. In fact, we can think about this as the definition of what we mean by a vector. A vector is rotated. Okay, it has a direction. And it thus must satisfy, so I can say that Vx and Vy and Vz are three components of a vector operator, like position or momentum, in 3D space, if it satisfies these commutation relations. v will be rotated. That is to say, I will take the vector v and rotate it by this amount. So if I have three components that satisfy that, we call it a vector operator. We're going to talk about this a lot next semester when we talk about things like electric dipoles and magnetic dipoles and quadrupoles. We'll talk about tensor operators. Won't that be fun? So, of course, angular momentum itself is a vector. Which means that it must be the case that this is true. Sum over k. And these are the fundamental commutation relations of what we call the Lie algebra for rotations. That is to say, there are three generators. There's a generator of rotation around x, a rotation around y, and a rotation around z. But they don't commute. If you do a rotation around x, followed by a rotation around y, that's not the same thing as doing it in the opposite order. Let's try the experiment. Here's something I'm going to rotate. I'm going to rotate it by, say, 90 degrees around the x-axis. And then rotate it by 90 degrees around the y-axis. Okay? See what it looks like? Now let's do it the other way around. Let's first rotate it around the y-axis, and then rotate it around the x-axis. It's a different thing at the end, right, before we have this. So rotations around different axes don't commute. That's true just because of the three-dimensional nature of space, but that has implications in quantum mechanics because the generators of rotations are observable that don't have simultaneous eigenfunctions if they don't commute. We cannot simultaneously specify eigenvectors that have a definite angular momentum along, say, x and y. What we can do is, if we look at the total angular momentum, so this is the square of the angular momentum, then you showed, and we know, if you've done it in your earlier, that this commutes with any one component. So the magnitude of angular momentum is not changed under rotation. That makes sense. That only the direction is changed under rotation. So I can simultaneously specify an eigenvector of some component and the magnitude, but not all of them. Okay? And what this says, of course, is that we have the fact that this is true, for example, Lx commuted with Ly is I h bar Lz, implies that the uncertainty in Lx and uncertainty in Ly can never be zero in general, or it must always be bigger than or equal to this. So we have a kind of uncertainty principle. Finally, what can we say given what we know so far? So we've shown, based on our analysis so far, when we're talking about orbital angular momentum, right? Thing having to do with the motion in three-dimensional space of a particle, that there are eigenstates of LZ, and those eigenstates have quantum numbers that are given over there, where n are integers. Moreover, we know that the magnitude of angular momentum can be simultaneously specified with one component, say the z component. So this gives a picture that we have of the possible angular momentum vectors.
Should there not be h bar squared over 4?
Blah, blah, blah. Yes, that is correct, indeed. Hold on a second. It's got to be this square then, yeah, because this is, what I was writing was, yeah, that's right, that's right, because this is my units. So let's just quickly sketch the possible angular momentum vectors. So let's say we have a definite magnitude. So it's an eigenstate with some eigenvalue of LZ. So it lives, the magnitude of the vector lives on a sphere. Along the z-axis, I can only take on integer values. So for example, I might have this value, I might have this value, I have that value. I have this value. So what am I drawing here? So I'm drawing different projections along the z-axis. These vectors have a definite projection along the z-axis, but an uncertain projection in x and y. I can't simultaneously specify the projection along z and the projection along x and y. It lives somewhere, in some sense, on this circle with these different projections. This is in really old-fashioned 1920s language. This used to be called space quantization. You'll see this still hanging around. It has nothing to do with quantizing space-time or anything like that. But it's a jargon that said the projection onto a direction in space was quantized. You'll see that jargon. What it really just means is that the vector, the angular momentum vector, has quantized projections along the z-axis in integer units. But the x and y projection is uncertain. So this would correspond to, for example, n equals 2, n equals 1, n equals 0, n equals minus 1, n equals minus 2. Okay.
Does the spacing between successive n integers get smaller and smaller?
No, it's equal.
But so I'm guessing you're exaggerating the spacing here, because
Yeah, they're equal. They're meant to be equal. It's just a bad drawing. All right. We will continue next time.
Yeah.